Okay, guys. Today we are going to start chapter number 6, which is stability. Okay. So in this chapter we will see कि हम कैसे चेक कर सकते हैं कि हमारा जो सिस्टम है वो स्टेबल है कि नहीं है. ठीक है. तो there are some requirements कि जी हमारा जो सिस्टम है it should be stable, right? So the definition of the stability is our system is stable if every bounded input yields a bounded output. So we call this statement the bounded input, bounded output, which is a BIBO concept. This is the definition of stability. Okay? So we will study about this in this chapter, and we will see either the system is stable or unstable. Okay? So a system is unstable if any bounded input yields an unbounded output. अगर कोई सिस्टम जिसकी इनपुट बाउंडेड है, if it gives you an unbounded output, then the system will be unstable. Let's summarize our definition of stability for linear time invariant systems. We say a system is stable if the natural response approaches zero as the time approaches infinity. ठीक है. Okay. So let us summarize our definition of stability for linear time invariant system. We say a system is stable if the natural response approaches zero as time approaches infinity. And a system is unstable if the natural response approaches infinity as time approaches infinity. And the third is a system is marginally stable if the natural response either decays nor grows but remains constant or oscillates. So there's some three conditions. We can say the system will be stable, will be unstable, and it will be marginally stable, right? So using the total response, we say BIBO, B bounded input, bounded output. A system is stable if every bounded input yields a bounded output. And a system is unstable if any bounded input yields an bounded output, right? So if we see physically, हम कहते हैं कि system about an unstable system whose natural response grow without bound can cause damage to the system. So that's why we say it is unstable. So there are some conditions कि जी हमारा जो stable system होगा वो क्लोज लूप है, ओपन लूप है, पोज कहाँ है और जीरोस किस जगह लोकेट होंगे. So we'll see all that. Excuse me. So we say that is stable system have closed loop transfer function with pose only in the left half plane. कि हमारा जो स्टेबल सिस्टम होगा वो क्लोज लूप ट्रांसफर फंक्शन होगा उसका, और उसके जो पोल्स होंगे दे विल बी इन अ लेफ्ट हाफ प्लेन. Right? We'll see, however, under some certain conditions, we can draw some conclusion about the stability of the system. First, if the closed loop transfer function has only this. So if you look at the figure number 1, which is a stable system, input we हमारे पास है R of S, we have output C of S, we have a negative feedback, and we have the gain of the system, which is 3 over S into S plus 1 into S plus 2. Right? So if we solve this system, we will find out कि हमारे पास इसकी पोल्स की लोकेशन हमारे पास कितने पोल्स हैं हमारे पास? 3 पोल्स हैं हमारे पास, right? And there is no zero. So the pole's location is there. So this is J 1.047 and another one is minus iota J 1.047 and the third pole is on minus 2.672, right? And if we check the response, we will have this kind of a response given in the figure here. We have another system and we call that this is unstable. Why it is unstable? Because two of the poles are on the right hand side of the plane, S plane. So when any of the system's pole is on the right hand side of the system, it is called unstable system. And if you look at the response is not stable. So this is a closed loop, but the system is unstable. Okay. To check the stability of the system, we have a new method which is called Routh-Hurwitz criterion. So in this section, we will learn a method that uses stability information without the need to solve for the closed loop system poles. So using this method, we can tell how many closed loop system poles are in the left half plane, in the right half plane, and on the j omega axis. And we just say how many, not where are the location, what will be the location. Okay, so we can find the number of poles in each section of the S plane, but we cannot find their coordinates. This method is called the Routh-Hurwitz criterion for stability, and it was developed by Routh in 1905. So this method needs two steps. Number one, generate a data table called a Routh table, and number two is interpret the Routh table to tell how many closed loop system poles are in the left half plane or in the right half plane or on the j omega axis. Right? So in this section, we will interpret a basic Routh table, and in the next section, we will consider two special cases that can arise when generating the data table. तो इस सेक्शन में हम लोग सिर्फ चेक करने लगे कि राउथ टेबल कैसे जनरेट होता है और उसको हम कैसे सॉल्व करते हैं. इसके अंदर कुछ स्पेशल केसेस होते हैं इन द नेक्स्ट लेक्चर वी विल टॉक अबाउट दैट. ठीक है. आप लोगों को आवाज आ रही है मेरी?
यस सर.
जी सर.
यस सर, आ रही है सर आवाज.
यस सर.
ओके.
यस सर.
अब हम क्या करने लगे हैं? वी आर गोइंग टू जनरेट अ बेसिक राउथ टेबल. ठीक है. इफ यू लुक एट द फिगर नंबर 6.3, तो हमारे पास क्या है कि हमारे पास एक इक्विवेलेंट क्लोज लूप ट्रांसफर फंक्शन गिवन है जो कि हमें शो कराता है द ब्लॉक डायग्राम. वी हैव इनपुट आर ऑफ एस, वी हैव आउटपुट सी ऑफ एस, एंड वी हैव द ट्रांसफर फंक्शन एन ऑफ एस ओवर a4s raised to power 4 plus a3s raised to power 3 plus a2s raised to power 2 plus a1s plus a0. ठीक है. So because we are saying कि जी Routh-Hurwitz table जो है, Routh-Hurwitz table, it focused on poles of the system, so we are very interested in the denominators. ठीक है, तो हम क्या करेंगे, हम सबसे पहले इसका टेबल जनरेट करेंगे, and then we will start labeling the rows with powers of s from the highest power of the denominator of the closed loop transfer function towards s naught. And then उसके बाद हम लोग coefficients find out करेंगे with the highest power of s in the denominator and list horizontally in the first row and every other coefficients in the row. In the second row, we will list horizontally, starting with the next highest power of s, every coefficient that was skipped in the first row. And we will put all the entries in as follow. Okay. So if you look at the table here, we say S4 excuse me guys. So if you look at the table here, we see that the equation S4 A naught S4 towards S naught is given here, and in the first row we will write the, you can say कि हम लोग even numbers को लिखते हैं, that S4 is equals to A4, A2 and A0, and in the second row we just write it down as which we have skipped in the first row, A3, A1 and A0. So this is the table that we have to make, and then A, S square, S1, S naught, we have to solve them further. So how are we going to solve them? We will see in the 6-point table, table 6.2. So how are we going to do that? ये तो हमारे पास आ गए A4, A2 and A0 and A3, A1 and 0, and then we'll go further. So we will have a mod that A4, this one A4 and A3, A4 and A3, and from the second column A2 and A1 in this one, and divided by जो हमारे पास S3 का जो previous उसकी value होगी. तो हमारे पास S4 का value है A4 and then A3 here, and then A2 and A1 divided by A3, and this is equals to, we call it B1. तो हमारे पास जो भी values होंगे, numbers होंगे बाद में, we will put them and we'll find out the value of S2, S is power 2. So here we have B1. इसी तरीके से next column में हमारे पास हम A4, A3 and then we'll take it as A0 and this power 0. तो ये हमारे पास आ गई divided by A3, this one, and उसके बाद फिर अगले में हमारे पास फिर A4, A3 and साथ में 0 0, और ये हो गया हमारे पास, ये आ जाएगा 0 के. We know that how to solve them, like this one and that one multiply by minus A2 or A3. So we know that how to solve them. So in S1 we say A3 and B1 and A1 and B2 here divided by B1 is equals to C1. So C, after B we'll say is C. We consider it C1. ठीक है, तो इसी तरीके से ही नेक्स्ट जो हमारा कॉलम है उसमें we'll put A3, B1 and the next one A0 and 0. Sorry, 0 and 0 because we are taking row number 2 and 3. Okay, so B1 is equal to 0, and this one again we have A3, B1 and then so on 0 0. So that will be equals to automatically 0. So if we come to x raised to power 0 here, we'll consider B1 C1 into in a column B2 0 here divided by C1, this one, this will be equals to, we consider it's D1, right? The same process you have to complete it for D2 and D3, right? And then we have to solve all these questions. So we'll write it down here is, we can say this is B1 and then B2 and then 0, and then S1, in S1 we say C1, 0 and then 0, and in S0 we say D1, 0 and 0. So this is the way you can complete your table. So this is the complete Routh table here, right? ये कहलाता है Routh-Hurwitz table. Now अब हम क्या करते हैं? Now we'll solve example number 6.1 from the book Control System Engineering by Norman Nice. I'm using a 6th edition. Right. So here we will see that how to create a Routh table. ठीक है, और हमारे पास कोई ना कोई transfer function given है. So the problem is, make the Routh table for the system shown in the figure 6.4a. So this is 6.4a table. This table is a 6.4 table, and what we will do is we will create a Routh table with this transfer function, right? First of all, when we solve this table, we have to solve this. We have to solve this and find a transfer function. Because this is a feedback system, we have to solve this feedback first, right? So if we solve that, we'll find out the equivalent closed loop system, which is in a figure B, right? So this is what we have here. We have find out, because this is a negative feedback, so we have to solve through the feedback formula, right? Okay, now we have the same with, if we have the question here, which is S3 plus 10S square plus 31S plus 1030, right? So in Routh table, because we are finding poles, so that's why we are focusing on denominator. We have nothing to do with the numerator, because we are not talking about zeros. In this section, in this question, even we know that there is no zero. So we have this value 1, 31 and 0, right? If you look at this one, 1, 31 and 0, and then in the next row it will be 10, 1030 and 0. So here we can see, so 1, 31 and 0, and 1, 1030 and 0. If it can be divided by any of the number in the row, we can do that, but in a row, not anywhere else. तो हमारे पास है 10, 1030, तो हम इसको divide कर लेते हैं 10 पे. So this will be 1, this will be 103, and it always also remains same as 0. ठीक है. अब what we have learned in the Routh table is कि हम लोग ये देखेंगे कि जी रो 1 एंड रो को कंसीडर करते हुए will move further. तो हमारे पास है जी 1 and from row to 1, so we'll write it down row 1 and to 1, and then the next one 31 and 103, 31 and 03 on the divided by the value of the row number 2's value. So this is 1 is equals to, जो हमने कहा था B1, so this will be equals to B1 minus 72. ठीक है. So now move further towards this one. So here we will say 1 and 1 into 0 and 0, right? So this will be 1. There is a mistake in this here. So it will be 1 and 1 and 0 and 0. So this will be equals to automatically 0, right? So here again 1 and 1 and 0 0, so on, it will be 0. So now come to forward towards S naught here. So now we'll take 1 and minus 72. So 1 and minus 72, and from this it will take 103 and 0. So 103 and 0 divided by the last row value. So this is minus 72. So here we write minus 72. So this will be 103. Okay, and the same process with the same 172 and then 0 0 and this 0 0. So this will be equals to 0. Okay, so next, from the first row of the table, using the coefficient of the denominator of the closed loop transfer function, we start the coefficient of the highest power and skipped every other powers of s. Now from the second row with the coefficient of the denominator skipped in the previous step, subsequent rows are found by with determinants as we have determined in the table number 6.2. So for convenience, any row of the rows table can be multiplied by a positive constant without changing the value of the rows below. This can be proved by examining the expression for the entries and verifying any manipulative and any multiplicative constant from a previous row cancels out. In the second row of the table 6.3, for the complete, the rows was multiplied by 1 over 10. We see later that the must be taken not to multiply the row by a negative constant. So this is the way we can find out the table of rows table. Okay. अब हमने टेबल तो हमने बना लिया, ठीक है. So we have made a table, rows table. ये टेबल तो हो गया हमारा कि हमने टेबल उसको हमने कैसे उसको डिजाइन किया, ठीक है. तो उसके हमने सारे रूट्स फाइंड आउट कर लिए. नाउ वी हैव टू सी कि जी सिस्टम इज स्टेबल एंड अनस्टेबल. हमें कैसे पता चलेगा कि जी इसमें सिस्टम स्टेबल है या अनस्टेबल है, ठीक है. सो लेट अस हाउ टू इंटरप्रेट इट, कैसे इसे इंटरप्रेट करते हैं, ठीक है. So the basic rows table applies to the system with poles in the left and right half planes. Systems with imaginary poles and the kind of rows table that results will be discussed in the next section. So simply stated, the Routh-Hurwitz criterion declares that the number of roots of the polynomials that are in the right half plane is equals to the number of signs changes in the first column. कि आपके फर्स्ट कॉलम में जितने भी आपके नंबर ऑफ साइन चेंजेस होंगे वो इक्वल होंगे कि आपके नंबर ऑफ रूट्स कितने हैं, इन द रूट्स कितने हैं पॉलिनोमियल के जो कि आपके राइट हाफ प्लेन में है, ठीक है. कि आपके साइन चेंजेस कितनी बार हुए हैं इन द फर्स्ट कॉलम. So if the closed loop transfer function has all the poles in the left half of the S plane, the system is stable. ये तो हमने ऑलरेडी पढ़ लिया है कि हमारे अगर पोल्स जो है वो लेफ्ट हाफ ऑफ द S plane में होंगे तो हमारा सिस्टम स्टेबल होगा. So if the system is stable, so thus the system is stable if there are no sign changes in the first column of the rows table. कि अगर रोज टेबल में कोई एक भी चेंजेस साइन का चेंज नहीं होगा then the system will be stable. साइन चेंज मींस के the value will be negative or positive, ठीक है. अच्छा, the first sign changes occurs when 1 in the S2 row into minus 72 in the S1 row. The second occurs from minus 72 in the S1 row to 103 in the S naught row. So in this case, the system of figure 6.4 is unstable since two pole exist in the right half plane. ठीक है. तो हमारे इस केस में हमारे पास क्या होगा कि हमारे सिस्टम होगा अनस्टेबल होगा क्योंकि हमारे पास दो साइन चेंजेस आए हैं, ठीक है. So when we have two sign changes in this transfer function, so we will have a system unstable, ठीक है. Okay, so that's it for today.